You've probably heard the term neural network thrown around all the time, right? It's behind everything from AI art to self-driving cars. But what is it, really? Well, in this explainer, we're going to build one from the ground up, and we'll start with something you do every single day without even thinking about it.
Let's kick things off with something super simple. Take a look at this. It's a pretty sloppily handwritten number 3, and it's at a really low resolution. Your brain, though, it knows it's a 3 instantly. You don't even have to try.
And that's where things get interesting. For you, this is a piece of cake. But just imagine for a second that you had to teach a computer how to do this with old-school programming, with a bunch of if-then rules. It would be an absolute nightmare. How could you possibly write down a set of rules that covers every single weird way someone could write a 3?
So if writing a giant list of rules is a dead end, we need a different plan. What if, instead of us programming the rules, we built a system that could figure them out on its own? A system that could learn. That right there is the big idea behind something called a neural network, an approach that's kind of inspired by how our own brains work. Now, I know the word neuron sounds a bit intimidating, maybe brings up biology class flashbacks, but for what we're doing, it's actually incredibly simple. Don't think of it as a brain cell, just think of it as a little container that holds a number, specifically a number between 0 and 1. We call that number its activation. You can kind of picture it like a dimmer switch. 0 is completely off, 1 is fully on.
So, these neurons, we organize them into layers. The very first layer is our input layer. Since our image has 784 pixels, we have 784 neurons, and the activation of each one is just how bright its pixel is. Then, all the way at the end, we have the output layer. This one has 10 neurons, one for each possible digit, 0 through 9. Whichever one of these neurons ends up being the brightest, with the highest activation, that's the network's final answer. And sandwiched in between, that's where you find the hidden layers, which is where all the real magic starts to happen.
But why layers? What's the point? Before we dive into all the math, let's just talk about the intuition here. What are we hoping these layers are actually going to do for us?
The big hope is that the network learns to build up ideas one layer at a time. So the first hidden layer might look at all the pixels and learn to spot tiny little things, like small edges. Then the next layer might learn to combine those edges into bigger components, like a loop or maybe a straight line. And finally, the output layer can look at those components and say, hey, a loop on top of a line, that's a 9. It's building understanding from the ground up.
And the goal isn't just for a neuron to memorize one specific loop in one exact spot. No way. The idea, the hope, is that a neuron learns to recognize a concept. So any kind of loopy shape in that general area will cause that neuron to light up. It's learning an abstract pattern, not just a bunch of pixels.
Okay, so that's the grand plan. But how does it actually happen? How does the information from one layer get passed to the next? To get that, we need to pop the hood and look at the engine of this whole thing, the connections between the neurons.
It really all boils down to two kinds of numbers. Or you could think of them as little dials that we can tune for each neuron. First up, we have weights. Every single connection from a neuron in a previous layer has a weight. This basically tells our current neuron how important that connection is. It's how it learns what patterns to pay attention to. Then there's a single number called a bias. Think of this like a little nudge. It determines how easy or hard it is for the neuron to get excited and activate in the first place. So what a single neuron does is basically a 4-step recipe. First, it gathers up all the activation numbers from the layer before it. Second, it calculates a weighted sum. It multiplies each of those activations by its specific weight and adds them all up. Third, it adds its own special bias to that total. And finally, because that sum could be, any number, big or small, it runs it through a function that squishes it back down to a nice, clean value between 0 and 1. And that result, that becomes its own activation, ready to be passed on to the next layer. Okay, so we've looked at how just one neuron does its thing. Now let's zoom back out and really appreciate the scale of this machine we've just put together. If you actually count up all of those weights and all of those biases in our simple little digit recognizer, you get a pretty wild number, almost 13,000. Yeah, that's how many little dials and knobs are in this machine, and each one needs to be tuned perfectly.
So when you step back and look at the whole shebang, a neural network really isn't some kind of magic black box. It's just a function. I mean, it's a ridiculously complex function, for sure, but that's all it is. It's a process that takes in 784 numbers, our pixels, and after all those calculations, spits out 10 numbers, our guess.
And that brings us right to what learning actually means in this world. When you hear that a network is learning, all it really means is that we are making the computer try to find the perfect setting for every single one of those 13,000 knobs, so that the function consistently gives us the answer we're looking for.
So, we've built the machine. We understand its parts, its layers, its weights and biases. We see how it goes from a grid of pixels to a final guess. But that leaves us with the biggest, most important question of all, doesn't it? How on earth do we actually teach it? How does a computer figure out how to set all 13,000 of those knobs just right simply by looking at examples? Well, that is the whole challenge of training, and that's a story for another time.